Okay, welcome friends. We will continue with our discussion on heat pipes. If you recall, last time we started to derive an expression for the maximum amount of heat that can be pumped by a heat pipe from its evaporator to the condenser end, and we named it. It is known as axial power rating. So, if you recall, we had drawn this schematic over here, which I am showing, and we said that in order for the heat pipe to function, the maximum capillary pumping head, which is provided by the wick, must be able to overcome the total pressure drop of the fluid as it flows through the heat pipe. And how does it flow? It first vaporizes, and then the vapor flows through the core, comes to the other end where it condenses, and then in the liquid form it flows back through the wick. So, if I say that my maximum capillary force, if I write that, or the capillary pumping head, if I write it as delta Pc, and I say this max must be able to overcome, so must be greater than equal to the different pressure drop that the fluid faces as it flows through the different sections of the heat pipe. So, what are those? So, the first one I am going to write it as delta P L. What is delta P L? This is for liquid flow through the wick. Okay. Then I will say delta P V. Why? What is this? This is the vapor flow through the core. Okay, what else? See, this is where the inclination that I have given deliberately of alpha comes into picture. Why? Because we also have a hydrostatic head because of gravity, and I am going to call it as delta Pg. I would say hydrostatic head. Now, why is this important? If you look at this diagram itself, see, as the liquid is pumped through the wick, it also has to overcome the force due to gravity, right, because the tendency of the liquid will be to come down along the direction of gravity, and the capillary force pumping head has to prevent that also and force it to flow in the opposite direction, right. So, that is the hydrostatic head, clear. So, what we are going to do next is we are going to look at expressions for each of them and then try to equate that. Okay. Starting with one by let us start one by one. The first one we are going to talk about is what we said, delta P L. Now, what is this? This is again liquid pressure drop through the homogeneous wick. Now, for this one, what we will use is we are going to use Darcy's law. Henry Darcy is one of the pioneers of flow through porous media. Again, the wick is a porous material. So, we are going to use Darcy's law, which states that the pressure gradient dP dx can be given as mu u over k, in this case mu L. Okay. Now, what does this mean? Where mu L is of course the viscosity of liquid, UL is velocity in that direction. Since we are saying dP dx, we have used u, velocity of liquid, and K, this is important, is known as permeability. Okay. And typically its dimensions is meter squared. Okay. So, this is Darcy's law. So, if we use it here, then we can write it as, therefore, delta P of L for our heat pipe can be written as mu L, okay, times L effective, because this is delta P, we have integrated over that length, divided by the permeability of the wick, I am writing it as Kw, and then what is left is the velocity, which I am going to write it in the form in terms of mass flow rate. I am going to write it as m dot, and why I am writing it as m dot, it will become clear later, divided by velocity is mass flow rate divided by density times area. So, rho L times AW. Okay. So, AW here is cross sectional area of the wick, okay, again denoted by meter squared, okay. Kw permeability of wick, also denoted by meter squared, and the rest of it is standard definitions, we all know that. M dot, let us call it mass flow rate given by kg per second. Okay. Next is, this is number 1, and so we have got this expression. Let us box it. 2. Next one we are going to call is delta PV. What is delta PV? So, that is the vapor pressure drop. Okay. And this one we can write it, this is pretty well known to us, our standard F L effective by D rho, let us write it as V over here, V bar squared by 2. This is our standard definition for steady incompressible flow through a pipe, right. And this again we can write it as, what is F? F for flow can be written as 64 over Reynolds number okay, or if we expand Reynolds number, 64 viscosity of the vapor divided by density of the vapor times the mean velocity times d, which is the inner diameter of the core, right. So, therefore, let us put this back here and write it as 32 mu v times V bar L effective over, let us call it as dV, because diameter of the vapor core dV squared, or finally let us box it in this way, or delta PV is going to be 128 mu V m dot L effective divided by rho V pi dV to the power 4. Let us box it. Why, what have we used? We have used V bar as m dot over rho V pi by 4, sorry, dV squared. Okay. The next one, which is number 3, is the gravity force, delta P G. This is pressure difference due to hydrostatic head which for our figure can be written to be delta P G is equal to rho G L sin alpha. Okay. So, let us put these things all over again. This is what we wanted to have, okay, delta PL, delta PV, delta PG, and we have expressions for all three, delta PL, delta PV, delta PG. Okay. So, the final thing that is remaining is the left hand side. What about the capillary pumping head? And I am going to use a different thing here. Capillary pumping head or delta PC. So, the driving force in the wick is what? The driving force in the wick is surface tension, right. So, you remember from our high school, delta P is 2 sigma over RC, right. Sigma is the surface tension coefficient for a particular bubble of bubble inside water. We had done all these derivations. So, I am not going to go into those details. So, what I will write now is just the expression for delta P capillary head. Okay. So, what I am going to write is, to obtain the capillary driving force, I can write it as, we are going to use some assumptions. I am going to write it as 2 sigma L cos theta R C. So, what all have we used? Okay. So, what all have we used is the following. We have used definitely wetting surface or hydrophilic surface, otherwise no point using a hydrophobic surface in a wicking material. So, that is obvious. Okay. RC is the mean effective radius of the wick. Okay. Yeah, that is pretty much it. This is all that we have studied. Of course, we also know that for a perfectly wetting surface, cos theta equals to 1 or theta equals to 0. So, wetting angle is 0, perfectly wetted. Okay. So, this is, we have assumed a wetting surface, but not a perfectly wetting surface yet. So, what are we going to do now? We are going to use these 4 expressions that we have derived and put it back into our momentum balance or the pressure balance, which we had written as what? Delta P C max must be greater than or equal to delta P L plus delta P V plus delta P G. Now, normally the vapor pressure drop, which is delta P V, is much less than delta P L. Okay. In other words, vapor pressure drop is negligible compared to liquid pressure drop to the wick. So, therefore, what we get is delta P C max, which is 2 sigma L cos theta over R C, must be greater than equal to mu L, L effective, m dot rho L Kw Aw, we all know this, this is coming from Darcy's law, plus, let me write the thing and then we will strike it to 0, mu v L effective m dot rho v pi dv to the power 4 plus rho L g L effective sin alpha. Okay. And what we said is this we will set to 0. Okay. And let us also set this to equality sign, because this is what it has to be greater than or equal to. So, at a minimum it should be equal to, and what we can write therefore is this gives us m dot is equal to 2 sigma L cos theta over R c minus rho L g L effective sin alpha times rho L Kw Aw mu L L effective. Okay. So, therefore, what did we want? We wanted to have the heat transport capability, which is APR, Q is going to be m dot HFG, because this is the mass flow rate that is getting vaporized at the evaporator end. Okay. So, therefore, this mass flow rate times the latent heat of vaporization is going to give me the total amount of heat that can be removed, and this can be shown to be equal to let me write it, it is a very beautiful expression that comes through, sigma L HFG over mu L times AW Kw over L effective times 2 over RC, let me call it as Q max, 2 over RC. Why? Because I am talking about max, and maximum happens when cos theta equals to 0, oh sorry, cos theta equals to 1 and theta equals to 0. So, 2 over RC minus rho L G L effective sin alpha over sigma L. Okay. This is what we set out to come up to derive, and this is what we have got. Why did I say this is a nice expression? Look at this term in the first parenthesis. Okay. What is it? Rho L, sigma L, HFG, mu L. All of them are fluid properties. Okay. So, these are all fluid properties. What is the next one? AW Kw over L effective. What are these? This is the area of the wick, this is permeability of the wick, this is effective length of the heat pipe, right. So, these are the heat pipe properties of wick and geometry, and the rest of it is a combination. It has both fluid properties as well as geometrical properties. We can't help here much, but think about it over here. Let us look at this, the term alpha. When is this maximum? When alpha is equals to 0, right? No, not really. Why not really? If alpha equals to 0, you get something, but what is alpha equals to 0? It means perfectly horizontal. Remember, alpha, sin alpha can be negative also. So, this is not essentially a positive quantity. So, if sin alpha becomes negative, then actually this term becomes larger. And when will it be negative? That is when you have it perfectly vertical. So, sin alpha is minus 1, correct. So, when sin alpha is minus 1, which means that the heat pipe is vertical like this with the evaporator below condenser. Recall over here in this picture that I had drawn, this was condenser below, evaporator above. Okay. You actually have to tilt it, you have to tilt it like this and make it vertical, and that is when you will get maximum. Clear? So, again recall, this is maximum when sin alpha is minus 1, which means the heat pipe is vertical with evaporator below condenser. And why? Because in that case gravity helps the liquid to come through the wick from vertically downwards. Okay. So, this kinds of gives us, this was a mathematical analysis and gives us the maximum amount of heat transport that can happen inside a heat pipe. And again recall, this is a good definition definitely. Another thumb rule is, this is for a straight pipe, but many a times you saw some of these figures in a laptop or for de-icing, there are bends. Any time you have a bend, the transport capability goes down. Okay. So, with bends, with narrowing of cross section etc., the transport capability does go down, all right. Okay. So, quickly now let us go over to some of the limits. So, this is maximum heat transport capability, we have seen that, but what are the limits? Even here also, what are some of the limits that we can face? So, the first one we are talking about is the capillary limit. So, when the capillary pressure is too low to provide enough liquid to the evaporator from the condenser, and that leads to dry out the evaporator. So, which kind of comes from this analysis also, if the capillary pumping head is not enough, if the liquid cannot come down from the condenser to the evaporator, but at the same time you are supplying heat at the evaporator, what will happen? The liquid at the evaporator end will vaporize, go, but it will not come back. So, this will lead to dry out. Okay. So, dry out means the evaporator section is completely dry, you are supplying heat, but there is no liquid that is left to evaporate. Boiling limit. So, boiling limit is when the radial heat flux into the heat pipe causes the liquid in the wick to boil much higher or much more than what is allowed, and therefore, it leads to dry out. And this also comes from this Qmax. If you supply something which is larger than Qmax, then what happens? You are boiling the fluid at a higher rate compared to the rate at which you are getting back the liquid. Okay. So, as a result, what happens? As a result, you will soon have a scenario where the entire liquid in the evaporator has boiled off because your heat flux is high, but the liquid has not come back. This also leads to dry out. So, the same phenomenon, dry out, in one case happens, in the capillary limit happens because the wick does not have enough capillary head, and in the other case happens because you have suddenly your heat flux has gone up so high that the wick is unable to cope up and pump back the liquid. So, you do not have enough liquid left, in both cases you do not have enough liquid left to remove the heat or to boil off and extract the heat. Okay. Entrainment limit. So, this is interesting, this happens at very high flow velocity, vapor velocities, okay, the vapor velocity through the core, where what happens is, because of the friction between the liquid that is flowing through the wick and the vapor that is flowing through the core, the force between the two at the interface, it can so happen that some of the vapor which is flowing will try to drag a few droplets of liquid from the wick, tear them off from the wick and entrain it along the vapor core. Okay. So, that is called the entrainment limit. So, when the vapor velocity is very high, that can happen, some of the liquid from the wick can get dissociated from the wick and join the fast moving vapor as droplets in through and flow through the core to the evaporator section, to the condenser section. And the last one is the sonic limit, which also occurs because of the very high vapor velocity, because where it reaches sonic limit okay, where it reaches velocities which is similar to that of sound, and so that can lead to choking and a lot of undesirable effects as is shown here. It can sometimes happen during startup of the heat pipe. So, suddenly if let us say your heat source is not working, let us say in a laptop for example, and then you suddenly switch it on and the CPU is running at very high power, this may happen. But typically, you know, when we switch on a computer, it typically switches on in an idle mode, and then you start launching applications, and that is when the heat dissipation slowly gradually increases. Okay. So, but the sonic limit we need to be aware of what it is. Okay. So, that is kind of our discussion on heat pipes. Let us quickly end with a couple of other techniques. The first one is called vapor chamber. Vapor chamber, the way it happens, it is kind of the working principle is the same as that of a heat pipe, but it is a 2D structure. Okay. So, as is shown in the schematic, a vapor chamber can be a very nice heat spreader, for example, where if you have multiple sources of heat, here also it is a 2D hollow casing, and with a wick along the internal wall, and what is happening is the entire surface at the top is the condenser. Okay. So, again what happens, the heat goes, the heat is supplied over here through this heat source, the liquid drops boil off, goes to the condenser, so in this case flows up, goes to the condenser where it gets cooled down and is brought back through the wicking action. So, essentially it is the same as a heat pipe, except that the configuration is different. It is a planar 2D flattened profile with the same working principle, where one end of this plate, so it comes as a plate, one end is the heater, the other end is the condenser. All right. Micro heat pipes is where you do not have a wick, it is a wickless structure where it has sharp corners and bends and sometimes narrow grooves, and those themselves provide the capillary action, because the radius or the effective radius, the capillary radius and the hydraulic radius of the flow channel are comparable. Okay. So, this is also used especially in many of the small electronic applications it is used, not so much for waste heat recovery. And finally, we should also know something called thermosiphon. What is the difference between a heat pipe and thermosiphon? Okay. So, thermosiphon, the way it works is it is completely driven by density difference. One of the most common examples that I have seen is our solar heaters or solar water tanks, where what happens is the cold water gets heated in the solar collector, and because its density is lower, it goes to the tank, and from where we can get hot water. Okay. And then again the cold water comes back and heated in the loop. So, the entire flow happens due to density difference, completely natural circulation. Okay. It is completely passive, there is no wick, unlike a heat pipe where the flow back of the liquid, cold liquid, happens because of capillary action through the wick, and also there is a phase change. In a thermosiphon, there may or may not be a phase change, but in case of a heat pipe there has to be a phase change. Well, thermosiphon source typically also most of the times is associated with phase change, but again the basic difference is this flow is completely driven by density difference, and there is no pumping action due to wick, unlike in a heat pipe. All right. So, that kinds of brings us to an end on the topic of heat pipe. Again, to recap, we started by understanding what is a heat pipe, how it looks and how it works. Then we talked about a few applications in terms of waste heat recovery, we talked about gas to gas heat recovery, we talked about de-icing, we talked about applications in IC engines and gas turbines, and we also talked about application in electronics cooling, which is per se not strictly waste heat recovery, but it is more of a cooling application. We then went over to study and derive an expression that will help us quantify the maximum amount of heat transport capability of a heat pipe, and we saw that it depends on a variety of parameters, including fluid properties as well as geometry of the heat pipe as well as the wick properties. Okay. And then we also talked about some limits that a heat pipe may face. We talked about 4 limits: capillary limit, boiling limit, entrainment limit and sonic limit. Okay. And finally, we wrapped up our discussion by looking at vapor chamber, which is a 2D heat pipe, if you may call it so, in a flattened profile, and also thermosiphons, which works in many ways is similar, but works due to density difference and does not contain a wick. Okay. So, heat pipe again is a special heat exchange device. It is a continuation of heat exchanger that we were discussing before, but here we saw heat pipes, how it can be used for waste heat recovery. Okay. So, in the next class we will move on to another topic. Till then, thank you very much. Hope you enjoyed this and learnt some new things through this discussion on heat pipes, and next class we will learn something new. Thank you very much.